Hello everyone, welcome you all to the next session on relations and functions of class 12 mathematics. In this session, we'll solve the remaining problems from exercise 1.2. Here is the 8th problem for us. Let A and B be two sets. Show that f from A cross B to B cross A such that f of A comma B equal to B comma A is bijective function. Here we are given a function f from A cross B to B cross A, and the function is defined by f of A comma B equal to B comma A. That is, if at all you have an element called f of A comma B, the output will be the flipping of A and B. That is, A and B will be flipped as B comma A. This is the function defined here. Let's check whether it is a bijective function, for which we have to check the given function is 1-to-1 and onto or not. Let's start with checking of 1-to-1. Let's take two elements from the first set, that is A cross B, and let us name the elements as A1 comma B1 and A2 comma B2. So the elements of A cross B are A1, B1 and A2 comma B2. There is ordered pairs A1 comma B1 and ordered pair A2 comma B2. And let us take these elements in such a way that f of A1 B1 equal to f of A2 B2. Now when I mean f of A1 B1 equal to f of A2 B2, it means that B1 A1 is equal to B2 A2. This is because by the definition of the function, that is f of A1 B1 is equal to B1 A1 and f of A2 B2 is equal to B2 A2. So by this relation, we'll have B1 A1 is equal to B2 A2. Now we see that there are two ordered pairs which are equal. That is B1 A1 is equal to B2 comma A2. When we say these two ordered pairs are equal, it means B1 should be equal to B2 and A1 should be equal to A2. Only then you can call these two ordered pairs are equal. So this tells us that A1 equal to A2 and B1 is equal to B2. Now let us consider A1 comma B1. When I consider A1 comma B1, I can replace A1 by A2 because of the relation A1 equal to A2, and I can replace B1 as B2 because of the relation B1 is equal to B2. So we can see that A1 B1 is equal to A2 B2. So if f of A1 comma B1 is equal to f of A2 comma B2, we get A1 comma B1 equal to A2 comma B2. This tells us that f is 1-to-1. Now let's go for checking f is onto, for which let me take an element from the second set, that is B cross A. Now we need to find out whether every element in the second set has a pre-image in the first set or not. Of course, we know that every element will have it because B comma A is nothing but the flipping of A and B. So automatically we can find out an element A comma B in the set A cross B which satisfies the given condition. There doesn't need much explanation in it. And hence we can conclude that f is onto. Since f is 1-to-1 and onto, f is bijective. I hope you will be able to understand what we are trying to prove here. Let's move on to the next problem. The 9th problem of the exercise. Let f from n to n be defined by f of n is equal to n plus 1 by 2 if n is odd and n by 2 if n is even for all small n belongs to capital N. The capital N here represents set of natural numbers. As we have already seen some problem where we had capital R that represents real numbers, here capital N represents natural numbers. So we have a function f defined from natural numbers to natural numbers using the definition, that is f of n is equal to n plus 1 by 2. That is, if your n is odd, if at all your n is odd, it takes n plus 1 by 2, and when your n is even, it takes a value n by 2. So this is the definition of the function given to us, and we need to check whether the given function is bijective or not. Let's see. Let's check for 1-to-1 first, for which let me take two elements called n1 and n2 from the domain set, that is from the first set of natural numbers. As I normally do, I'll put it as a diagrammatic representation. Here it is. Yeah. Let me go for the diagrammatic representation. We have two sets, but both are of natural numbers. So here is the first set of natural numbers, that is the domain set, and here is the second set of natural numbers, that is codomain. Let me take an element 1, 2, 3, 4, 5 and so on from this set. Now if I take n as 1 here, we know this 1 is nothing but your odd number. Now as per the definition of the function, if your n is odd, it takes the value n plus 1 by 2. So when you have n as 1, that is 1 is nothing but odd, so we have n plus 1 by 2 as per the definition, and this is equal to 2 by 2, and that gives us 1. So 1 from the first set is mapped to the element 1 in the second set. Now let's take the element 2 from the first set, that is we'll calculate f of 2. As 2 is an even number, when your n is even, it takes a form n by 2. So when you have n as 2, 2 is an even number, so 2 by 2 gives you 1. So you can see 2 also mapped to the same element 1. So even from this you can easily understand that two elements of the first set are mapped to same element of the second set. That is, the images are not distinct, and hence you can conclude f is not 1 to 1. In other words, f of 1 is equal to f of 2 does not imply 1 and 2 are equal. So if you have taken two elements, their images are not equal, or if you have taken different images, the pre-images are not equal. So this means that your f is not 1 to 1. Let's check whether the given function is onto or not. For which, again, let me go for the diagrammatic explanation. Here is the first set of natural numbers, and here is the second set of natural numbers. Now you can see from the previous diagrammatic representation that whatever number you take it, like 1 and 2 will be mapped on to 1. Similarly 3 and 4 will be mapped on to 2. We can have a cross check this one. 3 and 4 will be mapped to 2. Similarly 5 and 6 will be mapped to 3. This you can understand, or you can have a cross check. So you can see that all natural numbers in the second set, 1, 2, 3, 4 and so on, will definitely have a pre-image in the first set. 7 and so on, it keeps going. Now let's check for the first number. That is, if you take the first number 1 from the second set of natural numbers, you will have a pre-image here. Similarly, if you take 2, you will have pre-image. Actually, you will have two pre-images for all the elements, this and this. And if you take 3, you will have a pre-image. You will have two pre-images. So you can see all the elements in the codomain. That is, this is your codomain. All the elements in the codomain will have a pre-image, or they have actually two pre-images in the domain set, and hence the given function is onto. Let's explain this in an algebraic manner here. For that, let me take an element called small n, which is from the second set, that is from the codomain. Now let me check for the cases where your n is odd. That is, when I mean n here, for the odd integers which you're going to have it from the first set. Now if at all I choose n as odd, I can have n as 1, 3, 5, 7 and so on. Now when I choose n as 1, you can substitute here. You can go through here. You will have the elements. If you're going to have only the odd elements, let me put the odd elements alone in a different diagram. We can have 1, 3, 5, 7 and so on. This all will be mapped to 1, 2, 3 and it keeps going. So if I choose only the odd numbers, the first one is mapped to 1, 3 mapped to 2, 5 is mapped to 3 and so on. And you can generalize the n terms of the natural numbers, like 1, 2, 3 and so on. Here it ends up with the n natural numbers. 1, 3, 5, 7 and so on, it goes with 2n minus 1 numbers. So this is your general form of your number system here, and this is the general form. That is, n is the general form of your numbers in the second set. Now you can see any element in the first set takes the form 2n minus 1. So that's why you can see 2n minus 1 belongs to n. This n is nothing but your domain. So for any n belongs to n, this is your codomain. So for any n belongs to codomain, you can see 2n minus 1 belongs to the domain set such that f of 2n minus 1 is equal to n. That is, if f of 2n minus 1, when you say n is odd, this is actually your odd integer. So 2n minus 1, when n is odd, n takes the form 2n minus 1 and it is odd. So when you have an odd value, odd input for your f, the output is of the form that input plus 1 by 2. So you have 2n minus 1 is your input, 2n minus 1 plus 1 by 2. When you simplify this, you would get it as n. And hence you can see f of 2n minus 1 is equal to n and f is on 2. Similarly, when we consider the even integers, that is your even numbers, it is even set of natural numbers, you can see the number ends with, instead of 2n minus 1, you can see the numbers takes the general form of 2n, where your n represents your domain set of natural numbers. So if you have f of 2n, that is if your n is even, it takes the form 2n, and when you have an even number as an input, the output will be the even number divided by 2. That is 2n by 2 gives you n here. So f of 2n takes the form n, which again means your f is on 2. From the diagram, you can easily understand how to conclude whether it is onto or not. It is easily understood it is an onto function, but to put it in a algebraic manner, you need to distinguish odd and even numbers separately. So what happens when n is odd and what happens when your n is even? There are two cases available because your function is defined for both odd and even numbers. So for odd and even numbers, if your input is odd and if your input is even, both the cases we get an output. So whatever your output is, you are able to get either even number or an odd number from your first set. And this is the reason you can conclude your f is onto. So we have checked already for f whether it is an onto and one-to-one or not. We see f is not one-to-one but f is onto. So this tells us that f is not a bijective function. So with this we come to end of this problem. Let's solve one more problem of the same exercise. Here it is, the 10th problem of the exercise. Let a equal to r minus 3 and b equal to r minus 1. Consider the function f from a to b defined by f of x is equal to x minus 2 by x minus 3. Is f 1-to-1 and onto? Justify your answer. We have two sets here, one is a and the other one is b, where a is nothing but r minus 3. This means that a takes all values of real numbers except 3. When you have minus set containing the element 3, it means it can take every element of real numbers except 3. Similarly, b can take every element from real numbers except 1. If you have those two sets and the function defined from these two sets is given by f of x is equal to x minus 2 by x minus 3, and we need to check whether the given function is 1-to-1 and onto or not with the justification. So let's get started. Let us write what are our a, b and what are the function given to us. A equal to real numbers minus element 3, b equal to real numbers minus element 1, and f is a function defined from a to b by f of x is equal to x minus 2 by x minus 3. Now to check for 1-to-1, let's take two elements in the set A, that is x and y. So let x and y belongs to A such that f of x is equal to f of y. If we say f of x and f of y are equal, it means that x minus 2 by x minus 3 equal to y minus 2 by y minus 3. Because f of x is already given to us, which is nothing but x minus 2 by x minus 3, that we know it, and f of y is nothing but y minus 2 by y minus 3. We get this just by replacing x by y in our f of x. Where if you can check if your f of x will have everything in terms of x, whereas f of y will have the same expression but in terms of y. So we get this this relation, that is x minus 2 by x minus 3 equal to y minus 2 by y minus 3. Let's try to simplify this and see whether we can prove it is one-to-one or not. For which let us consider the equation x minus 2 by x minus 3 equal to y minus 2 by y minus 3. Obviously, the next step that we do here is cross multiplication. That is x minus 2 into y minus 3 equal to y minus 2 into x minus 3. Let's expand the terms on the left side and right side separately, and you can see the simplification. After all the simplification, we got minus x plus y equal to 0. That means minus x is equal to minus y, or x equal to y. Finally, we got x equal to y when we are using f of x is equal to f of y. So f of x equal to f of y implies x equal to y. So this means that f is 1-to-1. Well, I'm not explaining the simplification here because you can do it by yourself, and you have those steps on the board for you to cross-check your calculation. So we have concluded f is 1-to-1. Let's check whether f is onto or not. For which, let's take an element from the second set B, that is let y belongs to B, which is nothing but set of real numbers except the element 1. This means that y can take any element apart from 1. So y is not equal to 1. Now we have to find an element in the first set, for which let us take the element in the second set as y. That is, if at all we have a element, if at all we have two sets, say this is the first set and this is our second set. If this is our A and this is our B, if I give x as the input, your output is going to be x minus 2 by x minus 3, and let me call this as y. So let me have y is equal to x minus 2 by x minus 3, from which I'll try to get the value of x in terms of y. So as usual, we'll do the cross multiplication here. There's y into x minus 3 equal to x minus 2. On simplification, we can see x is equal to 3y minus 2 by y minus 1. This means that x takes the value 3y minus 2 by y minus 1. As we know, y cannot take the value 1. So this is possible because if y is equal to 1, the denominator becomes 0. So this expression doesn't make any sense when y is equal to 1. So we are able to find a number called 3y minus 2 by y minus 1 in the first set when you give x minus 2 by x minus 3 as your input here, or your y as an input. So this means that for every y in the set B, you are able to find an element in the set A. So we can easily conclude f is onto. So for every y belongs to B, there exists x belongs to A, such that f of x is equal to y. Therefore, f is onto. We have already proved f is 1-to-1, and we have proved f is onto also now. So f is both 1-to-1 and onto, and hence f is bijective. So we are supposed to check whether f is 1-to-1 and onto. We have checked it. F is both 1-to-1 and onto. So with this, let me conclude the session by giving you a few few problems for your homework. Here are the homework problems for you. Question number 11 and 12 of the exercise. That is, these are the two remaining problems in the exercise to complete it, and complete all the examples till example 14. So which will make you to complete the entire section. And the next session will start with the composition of functions. Until then, keep practicing and go through the sessions again and again for a better understanding and a better practice. Thank you.